Okay, guys, I want to solve this problem and which statistical test to use where. But nothing gets clear if you don't understand what uh, you're doing. Like, what are you testing? Are you testing for a hypothesis? And when you test for a hypothesis, you either look for a correlation. Okay, so first let's just see what the types of data are, and so let's start with the types of data over here. So as you can see, the types of data. Okay, now it's very important to know, like, so data is what is the input that we give for a study. So you want, like, most of our statistical test is to see, look for one of the following: look for association, look for correlation, look for risk, look for attributable risk, look for hazards. Okay, and to look for hazards. Okay, so now if you look at hazards, it's usually a categorical hazard. Like, hazard could be a categorical hazard like progression or death. So if you're looking at progression, you're looking at progression free survival. If you're looking at death, you're looking at overall survival. Now, usually what we do is that if you have categorical data, okay, then, like, categorical data would be a category. Like, for example, it would be male, female, blood group, chemotherapy yes, chemotherapy no. uh, or if you have to look at it as like dose of chemotherapy, then that would not be categorical, that would come into numerical. And but if you're looking at dose in terms of a numerical scale, it would be numerical data. But if you're looking at dose in terms of an ordinal, such as mild dose, moderate, and severe, which is predefined, then it still comes in categorical. So if you have two categorical data, such as treatment or no treatment, with progression or no progression, okay, then what we're doing is we're dealing with categorical data. And when we're dealing with categorical data, so we need to do a chi-square test. Chi as in categorical. If you're dealing with very small numbers, then we do a Fisher test. And if we are dealing with multiple categorical data, like for example, here we are dealing with mild, moderate, or severe, and then if we have like multiple influences and multiple categorical influences, and we want to like see what the outcome is with all these multiple like influences, then we do something called regression. Regression is to see which is the most influenced and the least influenced variable. And if it is ordinal and very clearly like defined, then in that case we would use the Man-Whitney U test or the Wilson-Saint-Rank Crucial-Wallis test. Supposing it is numerical data. Now, numerical data, the most important thing to understand is numerical data could, now numerical data means we need to organize it in terms of the mean of the data, the lowest value, highest value. Okay, and then we have to organize the mean with the median and the mode of the data. If the mean, median, and mode are all the same, then we would call it a Gaussian data. Okay, which is a typical data set. So it's very important to know if your data is normal or not normal, and because if you have a normal data, Gaussian data, then everything is beautiful. But in real life, you don't get that. So in continuous data here, we could, if it's we could use the with a normal distribution of data, such as height, weight, blood count, survival, or whatever in terms of finite values, and if it is continuous, then we put it in this Gaussian curve. And if we are comparing means, MEANT, we'll use the t-test. The t-test is meant for means of two groups. But if in a normal distribution data, and if it is like not nominal, we would use a different test. So, firstly, there is something called a Shipro-Wilks test, which checks if your data is nominally distributed or not. And here there is another Kolmogorov Smirnov, okay, like Smirnov or Smirnov. It compares the sample, whatever, how the data is distributed, if it is like a positively skewed or a negatively skewed data, okay. In positively skewed, the A, D, and O, the mean is greater than the median and is greater than the mode. It's positively skewed data. So the mean would be here, the median would be here, and the mode would be here, and the uh, sorry, it would not look like that. It would look like so if it is a not normal group, not normal distribution of data, then the statistician would apply a man-Whitney U test. Now, what are these tests? These tests are usually to calculate p-value, sample size, and other statistical variables. And so if there's a normal distribution of data, we would use t-test. We'd use the paired t-test for related groups. Now, what is a related and unrelated group? This is another big headache. Any matched group is a related group, or the same group, but in different intervals of time. That's what a related group is. And if the data is not normal and we have paired data, then we could use the Wilkinson rank test. ANOVA is to compare greater than two groups, analysis of variance, and matched data would be paired t-test again. Unmatched data would be U, back to the U. Unmatched would be U man-Whitney U test. So if you know that's not normal, then you do the U test. And if you want to see regression where there are multiple variables which are categorical or continuous, and we want to find out which are the dependent variables and predictors with multiple variables, we would use regression. Now, when would we use linear regression and when would we use logistic regression? So linear regression to predict or explain a continuous, dependent variable based on one or more independent variables. It will predict a continuous dependent variable based on independent variables. And we do logistic regression, which are to model binary or categorical outcomes. That needs a little bit more explanation, but so I wanted to show you this thing called Bradford Hill criteria, and this is the criteria that we have to like stick to some rules, right? Otherwise, everyone would do research however they want, and we want to see between the the exposure and the outcome, or between the intervention and the result, or like we want to see a group. There are a group of principles to establish evidence of a causal relationship between cause and effect. Now, this null hypothesis thing confuses a lot of students, but like let's just focus here. See, now we want to see if there is a strength of association, a strength of association does not imply causation, but the stronger the association, the more the evidence for causation. And then consistency, we want to see if something is consistently like impacting things. If it is specific, if there is temporality, where the cause precedes the effect. Uh, and if we want to see if we are measuring biological gradient, plausibility, where a mechanism exists by which the cause may, if there's plausibility, if there's coherence, if there's analogy, and basically uh, for the hypothesis, you need to like understand these things because, and there's something called a Kaplan-Meier curve. So it the graphical representation of probability uh, event probability versus time. Okay, and every time you have an event, it drops down. Okay, so it's useful for displaying time to event data, and so time to event and outcomes may include. So if this is what sorry if this is what your drug and your control, so your drug is decreasing the time to event, and then you can use a log rank test. But what I want to like conclude this first video with is the basics of statistical testing. So study rejects the null hypothesis. Study does not reject the null hypothesis. And in reality, what is there? So like supposing we want to predict that chemotherapy increases like life in cancer patients, and in reality it does increase life expectancy. Okay, and the null hypothesis is will be obviously that chemotherapy does not increase life. Correct. So the study rejects the null hypothesis. That means chemotherapy increases life. So it's a negative positive balance. But like let's just say chemotherapy increases life, and uh, and chemotherapy does not increase life. Okay, and in reality, chemotherapy really does increase life, or in reality, chemotherapy does not increase life, or chemotherapy decreases life. So now we want to test it. So if chemotherapy increases life, and if we like saw that chemotherapy increased life, but in reality, chemotherapy did not increase life, then that's an alpha error. So we saw an association that did not exist, and that's a false association, or the p-value is equal to the alpha error. Okay, and supposing chemotherapy did increase life, but in our study we saw that chemotherapy does not increase life, so we were blinded to it. So that's the beta error. We were blind to identifying our own study. So the power of a study is nothing but 1 minus beta. That's the power. And that's the type 2 error, beta. So if you understand beta, stating that you were blind and stating that there was no effect, okay, and stating that there was no effect, but actually there was. So when would that happen? When would you be blind to identifying something? When it is related to statistical power, which is you can eliminate being blind to anything by increasing the number of participants you test. So if you test more and more, increase the sample size and increase the testing, then you get a more power. So the more sample size you get, the more power you have. And that would, like, be my first video. I'll stop here.